Hi everyone. Today's tutorial is meant to discuss quantitative observations in a bit more detail. So again, observations can be qualitative, which means that I can describe them in words or give descriptions, or they can be quantitative, which means that they involve numbers. Now, in this course, we're going to see a lot of numbers this year, but not all numbers are treated the exact same way in chemistry or in science in general. For example, here on this first slide, we're going to be discussing briefly exact values. What that means is there are some numbers that we come across in scientific experiments that are exact. There is no uncertainty. Basically, they simply are what they are. And so an example of that would be this. Right here in this carton, we have precisely 12 eggs. There's no uncertainty. It's not that there could be 11 or 10 or 13. We can count. And when we count, we get a definitive number with no uncertainty. And so that's an example of a value that is exact. All right. Similarly, right, there are those values that we can use in calculations that aren't necessarily arrived at by counting, but they're just given to be exact. So for example, in this picture, I'm showing you a number of conversion factors between units of measurement. So for example, we know that there are 12 inches in 1 foot. Okay, it's not possibly 11, possibly 10 inches in a foot, or possibly 13 or 14. There are exactly 12 inches in a foot. Similarly, there are 3 feet in 1 yard. Okay, so once again, there's no uncertainty. The same applies to the metric system. There are 100 centimeters in 1 meter. Right? All of these things are known as conversion factors. Okay, and conversion factors are also considered to be exact values. Basically, there's no uncertainty. Now, that's not always true. All right, so for example, we have measured values. Okay, so for example, if I wanted to measure the length of this crayon, if I had to take a stab at it right now, basically I'd say possibly about 2.85 inches, maybe. And if I had to measure the length of the pencil in the picture, then maybe I'd say 15.9 centimeters. But if any of you were actually making the same measurement, you might disagree with me slightly. Maybe you would think that maybe this particular crayon actually is closer to 2.90 inches, or maybe this pencil is exactly 16 centimeters. Because there is some doubt as to the exact value of the length of each of these items, then basically these are uncertain values. These are measured values. And so the same also applies even if we're using a stopwatch. Using a stopwatch, basically it creates a little bit of uncertainty. Because even though there's a scale to read, on the stopwatch itself, there's always the issue of human reflex. Some of us are just a little bit faster than others. We might be a little bit more certain of having pushed that stopwatch to exactly end the time we're measuring, and some of us might be a little bit more uncertain of our reflexes. And so as a result, then this would also be an example of a value that's uncertain because, again, we're making a measurement. All right, the same applies when we're measuring liquid volume. All right, now again, we'll deal with this more in depth when we're talking about lab technique and lab equipment in a couple of weeks or so, but basically the proper way to read a graduated cylinder is by actually taking this position. And here's the level of the liquid within it. Maybe this person would say that this is exactly 50 cubic centimeters. But it's entirely possible that this person's lab partner might look at it and say, no, it's really 49.8. So again, because of this uncertainty, all right, measured values are never exact. And because of this, again, so measured values are never exact. And because of that, it often makes us feel a whole lot better if we repeat measurements. If we measure something more than once, then even if the measurement changes slightly, then at least we can take an average. At least we can have some idea as to how repeatable the measurement is, and we'll have a better idea of the quality of our data as a result. The problem is that when you repeat measurements, right, you can never expect to get exactly the same value all the time. So that means we're going to get a range of different numbers, or a distribution of numbers. And we need to be able to evaluate that distribution of numbers and decide, all right, is the data that I'm looking at accurate? Is the data that I'm looking at precise? All right, now, those two words are often very much confused. Again, this concept of accuracy and the concept of precision. So let's talk about accuracy and precision in a little bit of detail. Now, a common analogy that people use to discuss this concept of accuracy and precision is shooting arrows at a target. All right, now, if I'm an excellent shot, all right, if I'm an excellent archer, and I've been practicing for years, my arrows will land very close to the center of the target almost every single time, as in the target here in the lower right corner of the figure. Now, in this case, notice that each arrow is close to the center of the target. All right, that represents accuracy. If I'm close to that value that I was trying to hit, then that's accuracy. All right, notice that basically the shots, or the arrows, are also very close to each other. Okay, that's what we refer to as precision. If I can shoot an arrow and get it to hit the exact same spot over and over and over again, even if it's not the very center of the target, but it's the same spot that the arrow is hitting over and over and over again, then I would be considered to be very precise in my shooting. Now, if it turns out that in addition to that, I can hit the center of the target every single time, well then that would be an example of me being a very accurate shooter with a bow and arrow. Now, if you take a look at some of the other targets in the figure, for example here, all right, notice that the arrows landed very close to one another, but not necessarily close to the center of the target. So I wasn't hitting my target value, but I was getting the same exact shot to go in the exact same place over and over and over again. This is an example of a set of shots that was not accurate, because again, I didn't hit the center, but they're very precise because the arrows were very, very close to each other. Now, if you take a look at some of the top targets in the figure, in the top right corner, basically here, if I were to go and sort of average out, okay, where these arrows landed, basically they're all clustered pretty much equidistantly from the center. Here's the center, and the arrows are sort of around it. They're just not very tight around it. So we could consider these shots to be accurate, but not necessarily very precise. The arrows are sort of circling the center of the target, but they're not very close to each other. So we would consider this to be a set of shots that were accurate, but not precise. And then lastly, in the upper left-hand corner here, if we take a look at these shots, basically they're far from each other. So they're not precise. They're also far from the target. So they're not accurate. So again, bad accuracy and bad precision for this target in the upper left. Now, when we actually take this comparison and bring it into the chemistry lab, it's still the same idea, all right? If I collect a set of data, and that data set shows me that I'm very, very close to the value that I'm supposed to get, then that data set is accurate. But they're not necessarily very precise if the data points are far from each other. All right, so let's take an example of that. Suppose that I have a scientist actually measuring the density of seawater, okay? And let's say that the average seawater density is 1.029 grams per milliliter, okay? So the scientist measures the density of the sea, each group of scientists, I should say, measures the density of the seawater 3 times. And then they take an average. The average is right here at the bottom of the table. So the average for group 1, average for group 2, average for group 3, average for group 4. All right, if we take a look at the average density for group 1, then basically it is the closest to the target value of 1.029 grams per milliliter. So because of that, we can say that group 1 was the most accurate. Okay, but what about precision? All right, how are we going to take a look at the precision? One way to do that is to calculate something called a tolerance. Okay, the way that we do that is we subtract the highest value. Okay, we're going to take the highest value, subtract from it the lowest value of the data set, divide by 2. So, for example, for group 1, if I take 1.051 and subtract from it 0.998 and divide that by 2, so basically 1.051 minus 0.998 divide by 2, I get a tolerance of 0.027. And I'll write the tolerance up here. Okay? I'm going to repeat that for each of the other groups. All right? I'm not going to show the calculation for each one. Same idea. You're going to take the highest number, and you're going to subtract from it the lowest number, and then you're going to divide that difference by 2. For group 2, if you do this properly, you should get 0.001 as your tolerance. For group 3, you're going to get 0.027 again, just like the same as group 1. And group 4, you're going to get 0.006. Okay? Now, if you take a look, the group with the lowest tolerance, and what lowest tolerance means is that the numbers are clustered the closest together. There's the smallest difference between the highest value and the lowest value. That group was group 2. So group 2 was the most precise. Okay? So this is very important when we deal with scientific work in general, and also extremely important in chemistry. We have to be able to be aware of the quality of our data. Is our data likely to be accurate? In other words, is it close to the expected value that we're expected to get? All right? And is the data repeatable? Am I getting the same thing over and over and over again? Because if I'm not, basically if I'm getting values that are very different from each other, that implies that maybe an instrument that I'm using is broken, maybe there's something wrong with my experimental setup. The closer your numbers are to each other, then that implies that your equipment is working properly, whether or not you're making a mistake using it or not. Okay? So please work on the follow-up assignment that goes with this tutorial. If there are any questions, then by all means ask me tomorrow in class. During our application activity, our assignment, I'll be circulating the room to see how you guys are doing. Again, please feel free to stop me and ask me any questions you might need, and I will see you in class tomorrow.